To recapitulate, the demonstration starts with a simple 14-bit message, H, I, for high, represented by a 2-level square pulse encoding function, high for bit 1, and low for bit 0. The signal, as in its baseband form, is susceptible to additive noise in the same low frequency range of the baseband. The message signal is irretrievably lost in the transmission that is the sum of the message signal and the overwhelming noise. The most common technique in communications to overcome the baseband noises is to use a high-frequency carrier. The demonstration uses 9 kHz carrier and applies amplitude modulation with the message signal. With a high-pass filter, the message signal can be separated from the low-frequency baseband noises. However, in the case of additional interference signals with also high-frequency carriers, another filter is needed, a low-pass filter that still allows the message signal pass through, while attenuating the higher frequency interference signals. Both filters jointly form a band-pass filter that selects a frequency range around the message signal carrier frequency, but attenuates everything outside the band. The last step is to simply demodulate the signal, that is, to remove the carrier from the original message. The demodulation is done in the simplest approach with a diode to make the carrier oscillation unipolar. Then the high-frequency component can be simply removed with a low-pass filter, to restore the message signal back to its original form. The process is now complete. High-pass filter, joined with the low-pass filter, forms the band-pass filter. Output of the bandpass is connected to a diode to rectify the modulation. Look at the blue trace, for the signal before and after the diode rectification. After the final low-pass filter, the baseband form of the original message signal, which consists of square pulses for bit 1 and bit 0, is reconstructed. The process described here happens countless number of times in every second in the world, to make the internet work.